So basically, if some really important molecule in the cell needs nitrogen, chances are an amino acid is supplying it. It's like this mandatory pipeline for all the high-stakes nitrogen-containing machinery. Seems like the body's constantly sorting incoming amino acids based on urgency.
Precisely. They're essential for making stuff, but the supply has to be used for immediate needs, whether that's building proteins or making these specialized molecules.
Okay, so the body handles what it needs for proteins and specialized products. Makes sense. But we often eat way more protein than we need for just that, right?
Right.
Say after a big steak or a protein shake. What happens to the uh, probably substantial amount of amino acids that aren't used in those two ways, the leftovers?
Right. Since storage is off the table, they go straight to mandatory catabolism, immediate breakdown. They simply cannot linger in the bloodstream. And this loops us right back to that dual challenge of amino acids.
Oh, because breaking them down immediately forces the nitrogen issue again. The molecule splits, right? Two distinct parts.
That's it. The first part is that nitrogen component. This inevitably forms ammonia, and it must be immediately detoxified through that high-cost mandatory urea cycle. You can't get the energy out without dealing with the toxic part first.
And the other half, the part without the nitrogen, the structural leftovers. What's that carbon structure called and where does it go?
That's what we call the carbon skeleton. Sometimes you'll hear it called a keto acid. This carbon frame is actually what the body's interested in when it breaks down excess protein for energy. That's where the usable energy is stored.
I see. So once that structure is cleaned of nitrogen, then the body can finally treat it like any other fuel, a kind of purified energy unit.
Exactly. Once detoxified, that carbon skeleton gets funneled straight into other existing metabolic pathways. The same ones used to process energy structures from glucose or fatty acids. It's used for immediate energy production. The key difference is just that mandatory, non-optional detox step that has to happen first.
So the metabolic rule is absolute then. Use it for structure, use it for special stuff, or burn it right away. But no matter what, that nitrogen part means mandatory cleanup. The system allows zero inventory and zero lingering toxins, it seems.
And that brings us right back to the two things that really define amino acid metabolism. They're unique because of that nitrogen, which forces the urea cycle to exist and run. And they're unique because there's just no way to store them. They're valuable resources, sure, but they come with a high processing cost and absolutely zero inventory space.
Yeah, it paints this picture of amino acid handling as being less about, like, maximizing energy efficiency and maybe more about containment and safety. You can't save them, and they're toxic if you don't deal with them immediately.
That is the essential insight here, yeah.